Hey, welcome back AP Calculus students. Today we're looking at 5.3, connecting f prime and f double prime with graph of f. So the first thing we're looking at is the first derivative test. So a few notes here is if we find f prime and it goes from positive to negative, then we have a local max, and then if f prime goes from negative to positive, we have a local min. So what that looks like is, so remember, this is the graph of f, right? F prime is the slope. So if the slope goes from increasing to decreasing, then we know at that point we have a max. If it goes the opposite way, if it goes from decreasing to increasing, then we know we have a local min. All right, now the endpoints are a little bit different. So on the left end, let's say we have something that looks like this. On the left end, if f is less than 0, so if it's decreasing, so on this side it's decreasing, right? It's negative on the other side of our point, then we know we have a local max. Otherwise, if it were going the other way, say like this, if the points to the right-hand side of our left end point were increasing, positive, then we'd have a local min. And then same idea with the right end, but it's flip-flop because we're looking at the numbers to the right side, or left side of our right endpoint, excuse me. So if f prime is less than 0, then it's a local min. So notice this is decreasing, right? Excuse me, increasing. So this would be a local max. If we're the other way around, if the numbers on the left side were decreasing, then we have a local min. Okay, so let's go ahead and apply this stuff to our functions here. So x cubed minus 12x minus 5. So we do derivative with respect to x of our function. So we get 3x squared minus 12. 5 derives out. Right, so what we're going to try to do here is we're going to find our zeros, our critical points. So we're going to do plus 12 divided by 3 square root, so x is positive negative 2. Right, and what we can do here is we can make a chart. So 1 at negative 2, 1 at 2. Kind of like we did last time, right? So we're trying to figure out, all right, let's put some numbers in here. So let's try negative 3. So if I plug in negative 3 to my derivative, then I get negative 3 squared is 9 times 3 is 27 minus 12 is positive. Right? And then let's do one for the middle point here. Let's do 0. Well, that's going to be 0 minus 12, which is negative 12. So that's negative. And then on the other side, let's pick a 3 here. Again, 3 times 3 squared minus 12. It's going to be the same thing, right? It's going to be 27 minus 12, which is 15, which is positive. So from this chart, I know that there's going to be, because it's going from positive to negative here, right? It's increasing to decreasing. This is going to be a max at negative 2. And then there's going to be a min where it changes from decreasing to increasing. Okay, so the second part of this says to identify absolute. Because I know that this is a not a quadratic, but a cubic function. It's positive. It looks like this. So even though we located these two maxes and mins, the local ones, they're not going to be absolute. So these are just locals. So local min at -2, local max, or sorry, local min at +2, local max at -2. Okay, so same with the next one. It's a little bit tricky though. We could multiply the e to the x out, but that might just make it more difficult. Let's leave it in this factored form. So what we know about e to the x, this is always positive. Right, so it's not gonna mess with our values here. Right, so if we're trying to find where the zeros are, that part is gonna tell us where our zeros are. So let's do the derivative of that. It's going to be equal to 0 at, let's find the derivative first. Okay, so let's do the derivative of this whole thing. Okay, so this is a product rule. So u is x squared minus 3. du is 2x, v is e to the x, and dv is e to the x again. Alright, so let's put this all together. U dv plus v du, oops, 2x e to the x. Okay, and because e to the x is common, e to the x is common to both, we're going to do e to the x outside, then we have x squared plus 2x minus 3. Okay, so again, we said e to the x is always positive. We're not going to worry about that. We're worried about this side, this thing in here. So we're trying to figure out when this is equal to 0. So if we factor this, we're looking for what multiplies to get -3, adds to get +2. That would be +3, -1. So x equals -3 and 1. We make our table here, our chart. And we're going to determine our signs here. So we're going to plug it into here. So let's do -4. So -4 squared is 16 plus 2 times -4 is -8, so that's 8 minus 3. So this is going to be a positive in here. In between 3 and 1, let's use a 0 again. That's easiest. 0 plus 0 minus 3 is negative. And then any number bigger than 1, let's do 2. 2 squared is 4. Plus 2 times 2 is 4 again. That's 8 minus 3 is +5. So we have, let's change colors here again. Minimum when we go from negative to positive, so at 1. And we have maximum at -3. So let's go ahead and graph that. Let's just see what it looks like so we can determine if we have absolutes or not. Okay, so when we graph this, let's erase a little bit over here so we can make some room. What the graph of this looks like is this. So this one would be at the -3. this one would be at 1. So we can see definitely that negative 3 is not going to be an absolute, but the absolute minimum would be at 1. So this would be absolute, because there's no values below that. Okay, so concavity. Concavity just means the way it's curved. So notice that x squared, this is concave up, because this thing is shaped this way. This is concave down, because it's shaped this way. Now x cubed has two concavities. There's one part where it's concave down, right, because it's got this shape. But then there's another part here on the other side of that where it's concave up. So there's two different parts. So what concavity says is if we find the second derivative where it's greater than 0, it's concave up, or it's less than 0, it's concave down. So let's go ahead and verify. So if we did the first derivative, that would be 2x. The second derivative would be negative 2. I'm sorry, positive 2. So throughout this function, since the second derivative is positive 2, it's always concave up, which makes sense, right? Because a parabola for x squared is always concave up. Likewise, if we did negative x squared, which is concave down, first derivative is negative 2x, second derivative is going to be negative 2, so it's going to be concave down the whole way. Now the last one, x cubed. So first derivative is going to be 3x squared. Second derivative is going to be 6x. So notice that this is going to be concave down, right? If I put a negative in here, then it's always going to be negative. 6 times any negative number is going to be negative. So for all negative x's, it's going to be concave down. But if I put a positive in there, anything positive is going to make it concave up, because our second derivative will be 6 times a positive number, which is positive. Okay, so the last thing we want to do is determine concavity. I think it's the last thing. Oh no, not quite the last thing. Determine concavity on the interval. Okay, so, well, we kind of figured out x squared already, but let's go ahead and do it. So we're going to do the first derivative, and then we're going to do the second derivative. So we know that on the interval 3 to 10, we know it's always concave up, because it's positive. Okay, let's do the next one. First derivative, second derivative. Okay, now we got to think about on the interval from 0 to 2 pi. So what we're going to do here is we're going to start at 0. Right, when sign is 0, then it's 0. Right, so it goes 0, 0. Let's draw it out. Maybe that'll make it better. Okay, so this looks like our negative sign, right? Okay, so we know this is at pi and this is at 2 pi. So we start at 0, 0. It's negative all in here. So then what we're going to say is that it's going to be concave down from 0 to pi, right? So that's this whole section in there. And then because this next part is positive, it's going to be positive concave up from pi to 2 pi. And then if we go ahead and look at the normal graph, so what this would look like is it would be shifted up 3, but it would still be a sine graph, right? And if we check it, then we know that that's halfway. It's definitely concave down from 0 to pi, and then it's definitely concave up from pi to 2 pi. Okay, so on to the last one. We're looking at points of inflection. So if we're talking about concavity, we already pretty much know where the points of inflection are. So it's just where the concavity changes. So where it goes from down to up or up to down. So for this sine one, the point of inflection would be at pi because it changes concavity there. Okay, so it says find all points of inflection for y equals e to the negative x squared. So we're going to do, first thing we're going to do is we're going to find f prime and we're going to set it equal to 0. So e to the negative x squared, right? We're going to do the derivative. So that's going to be e to the negative x squared. We need to make sure we chain it though, right? So then we chain the x squared to be negative 2x. Right, so this is y prime. Now we gotta take that and derive it again. So this time we need to product rule it, right? Because we have this thing times this thing. So u is e to the negative x squared. We already found the derivative. du is going to be e to the negative x squared times negative 2x. V is going to be negative 2x. And dv is going to be negative 2. Let's change up our colors. So it's going to be, let's put this all together. U dv, so negative 2 e to the negative x squared plus v du, so negative 2x e to the negative x squared. We're trying to find out when that's equal to 0. So let's go ahead here and factor out our common factors. So I'm going to take out a negative 2e to the negative x squared from both of them. So in the first part we're left with 1. The second part we're left with x equals 0. So we're not going to be able to get a 0 from our negative 2e to the negative x squared part. But what we're going to be able to do is get a 0 from the second part. So that's going to be x equals negative 1. So the only point of inflection for this one would be at negative 1. Let me just make sure I did that correctly. Wait, did I do something wrong there? Minus 2x. Oh, I did something wrong there. Okay, wait. Okay, so again, sorry, I messed it up. So u dv is correct, negative 2e to the negative x squared. V du, I forgot to multiply this with this. So it's actually going to be 4x squared e to the negative x squared. So we're trying to find when this is equal to 0. We're going to do the same thing. We're going to take common factors out. So we're going to take our 2 e to the negative x squared, but inside we're still left with 2x squared from this part, and then a 1 from that part, so minus 1. Okay, so this part again, we can't make that part 0, but we can definitely make that part 0. So let's go ahead and solve it. 2x squared minus 1 equals 0. Okay, so then we divide by 2. So x is going to be equal to the square root of 1/2. Positive, negative. Okay, so these would be our zeros, which are our points of inflection. So we have one at positive, positive square root 2 or 1/2, which is square root 2 over 2, but we don't have to rationalize it now. And then negative square root of 1/2. Okay, that's it for today. Hopefully it wasn't too much. Good job.